All right, let's get started. So the first announcement is we're going to have the third exam a week from. It's a little quick, but we need to do them to kind of catch up to the delay from the hack, right? So the material for the exam, it's not going to be all the material we covered, but if we wait, there's just be just too much material on the third exam. There already is kind of a lot of material as it stands. So the third exam is going to cover the remainder of the chapter of torsion. So that is angle of twist, as well as the statically indeterminate torsional problems. And then the material we covered in the bending chapter. So that's sections 6.1 to 6.4, right? So flexure formula, and then shear and moment diagrams using both graphical and direct approach. And then also the material we covered in chapter 7 on transverse shear last week. So that's section 7.1, 7.2, and 7.3. All right. So today we're going to start on the combined loading chapter, but that will not be on the exam. All right. So all the material that's going to be on the exam, we've already covered already. All right. All right. Are there any questions on that? Let's see. Okay, there it goes. All right. Well, if not, then let's start with chapter 7. Or I'm sorry, chapter 8. So,
Professor, sorry that I interrupt you, but did I hear correctly? The final exam is only going to cover up to chapter 7?
No, the third exam, which is a week from today.
Oh, okay.
Okay. The final exam will cover the rest of the material, all right?
A week from today.
Okay. A week from today, so next Tuesday, all right? Where is the file? All right, well, I don't know. My slides are not opening for chapter 7, but chapter 8, but it's not really a big deal. It's chapter 8. Oh, there they are. Okay. All right. All right, let me mute everybody first.
Professor, sorry to ask one more time. So the exam's Tuesday, April the 13th, because on the calendar it says it's the 15th.
It's next Tuesday, okay? I don't know what date it is.
Okay.
You guys can figure that out, right? I don't know what date it is. It's next Tuesday. It's not next class, it's the class after, right? There's a revised lecture plan anyway that went up yesterday, so you might want to look at that. Oh wait, maybe I didn't put the revised one. I wrote it. Oh, you know what? I apologize. I thought I posted, but I might not have posted the new one. I need to do that. All right. There they are. All right, finally, here's the slides. All right, so this chapter 8, there really is very little new information in here. It's all applications of things we've done before. That being said, it actually is both one of the most important chapters in this course, as well as some students do find it the most challenging, because it really does require that you move beyond just the real simple plug and chug understanding of the material that we covered in axial, torsion, and bending, right? You have to really understand how forces contribute to axial stresses, how forces contribute to torsional stresses, how forces contribute to bending stresses, and kind of get your proficiency in that material beyond just like, okay, when I see a problem with a force, I put the force over the area. Okay, so it's an excellent chapter. Also, pretty much every mechanical engineering component that you see involves combined loading. Very rarely will mechanical engineers design components that are only in torsion, only in tension, only in bending. Almost always they're combined loading. Some of the other disciplines kind of have that luxury. In civil engineering, they do have structures that are like only in tension and stuff like that. But in general, for mechanical engineering, that's not the case. So it's absolutely essential. It's absolutely essential that you are able to handle these problems, but really probably more importantly, that you're able to look at how components are loaded and understand that that force is going to put a torsional stress on the body and a bending stress, or this force might put a axial end of bending, you know, and that's really critical as far as designing. Okay, even if you don't have to instantaneously get the answers, you have to be able to appreciate how loads do put stress. All right, so we're going to talk initially, you know, and this is pretty historical pedagogically. We'll talk today about thin wall pressure vessels, cylindrical and spherical ones. And then we're going to talk about combined loading problems. And again, one of the big things that we really want to convey is being able to visualize, and I use that term, you know, I guess it should be in quotes, but to realize how loading on components induces different types of stresses, bending, axial, torsion. Okay. All right. So let's go quickly through the pressure vessel bit. So there's two types of pressure vessels that we're going to consider here in this class. They're all thin walled. And so thin wall basically means that the thickness of the wall is probably, you know, like if we take this over the diameter, it should be less than, you know, like 1/10-ish or 1/5-ish, you know? If the thickness starts to become greater percentage of the overall diameter, now you actually are going to see stresses evolving through the thickness, and you usually have to use a different type of theory on that, which is a thick wall pressure vessel theory, which we're not covering here, all right? All right, so shown on this side is a thin wall pressure vessel that's in the shape of a cylinder. So this is a cylindrical thin wall pressure vessel. Sometimes you will see these with hemispherical caps, and actually the analysis here is the same for both flat capped thin walled cylindrical pressure vessels or hemispherically capped thin wall pressure vessels. And you'll see why. All right, so we're going to go look at a little differential element on this wall of the pressure vessel, okay? And, oops, this is in the way a little bit here. And so if we take this section here, that's sort of like between these two planes and draw it as here, you can see here is a free body diagram associated with this. So there is the pressure inside the pressure vessel. Here it's got a value of P. It's applying on to the inner surface of the pressure vessel, and that wants to obviously push it out, right? And that is resisted by the internal stresses in the walls of the pressure vessel. So if we were to look at that, right, you would see a free body diagram that kind of looks like this. The net force acting up here is the pressure over this projected area. So we can call that, here they're using dy. This will be the pressure times twice the radius. I forget what the book uses. I think they use radius. Oh, that's annoying. Oh, it's the diameter times dy, right? So this is the area that the pressure acts on, and this is the pressure. So that's the net force acting up. All right. Then balancing that are the internal forces due to the stresses in the pressure vessel. These are going to be the sigma 1 stresses. These are also called the hoop stress, because it's like the stress you would see in the hoop of a barrel. So this has a value of sigma 1, that's the stress, and the area at axon is the thickness, T, times the same dy distance out of the board. And up, half is here. And well, actually, it's T. And then this is also all right. So that's the force due to the internal stress. So if we do sum of forces in the y direction, right, we have P d dy equals 2 sigma 1 T dy. The lengths cancel out, right? And now we're left with that hoop stress, sigma 1, is equal to the pressure times the diameter over 2. Okay? And that's how we calculate the hoop stress. Now, the diameter technically is the inner diameter, but very often, like I was saying before, the thickness is so small in comparison to the diameter that even using the outer diameter doesn't introduce a significant error in this calculation, okay? But if you're given the outer diameter and the wall thickness, you should use the inner diameter in here, right? Because that's obviously how we've derived this, okay? All right, the second type of stress we got to look at is this stress, this sigma 2 type of stress. And I always do this, right? So yeah. Well, now I know I put that picture all over what I just did the derivation on. So I never know where I do the derivations. So well, excuse me. I guess I'll just leave it up there like a bit of a mess. I'll write over it. Okay, so here is the free body diagram to figure out the lateral stress, the sigma 2 stress. And here you can see we have, I'll draw it as like a cup. So the force acting on the back face due to the pressure is going to be the internal pressure times this circular area, which is pi times the diameter squared over 4, right? That's that area. So that's the total force acting on it. And then balancing it is going to be the forces from those sigma 2 stresses, right? So here we have sigma 2, and the area it acts on is this circumferential area of the thickness of the pressure vessel. So that area is going to be pi times the diameter times the thickness, right? So again, it's thin enough that we can approximate this area as follows, right? We don't have to use the diameter of the outer squared minus diameter of the inner squared, okay? And, we got half of that here and then half of that up here. And so now, if we do sum of forces in the x direction on this free body diagram, we are going to get pi times the pressure times the diameter squared over 4 is equal to those two lateral stresses added up, which gives me sigma 2 times pi times the diameter times the thickness, okay? So the pi cancels out. One of these diameters cancels out. And now we can get that the lateral stress, or I should say the longitudinal stress on this one, sigma 2 is going to equal the pressure times the inner diameter over 4 times the thickness. And I think I dropped the thickness in here somewhere. What did I? Yeah, I'm sorry. There should be a thickness down here too. I forgot to divide through by it, okay? And so those are those two stresses. So you get two different stresses for a cylindrical pressure vessel. You get the hoop stress here, which is the larger, and then you get this longitudinal stress. It's so difficult writing this out. All right, and you can see that sigma 2 is equal to 1/2 of the hoop stress, sigma 1. So you have two different stresses in the two different directions. This is a biaxial state of stress. And, this is our combined loading problem, because unlike other chapters where we just had the stress acting in one direction, here we have the sigma 2 stress, the longitudinal stress acting down the length of the pressure vessel, and that is orthogonal to the stress component sigma 1, the hoop stress, right? They're both normal stresses, but they act in different directions, okay? So for example, if you had a coordinate system aligned with that little differential element, where this is the x-axis and that's the y-axis, then the sigma 2 stress, the longitudinal stress, would be a normal stress in the x direction, and the hoop stress would be a normal stress in the y direction. But then obviously, you would have the same stress state whether you're here or you rotate up to the top. And in that case, you would have well, actually they do have the pressure vessel here. I should use the coordinate system that they have there. So if you use this component here, right? Here we have this being the y direction and this the z direction, as shown up here. So the normal stress, sigma 2 would be a normal stress in the y direction, and sigma 1 would be a normal stress in the z direction. But if we rotate up 90 degrees to the top of the pressure vessel, they will have the same values, but they'll be different components. If we were to draw that component at the top, you would have still sigma 2 in this direction. I'm sorry, that's sigma 1. You still have sigma 1 in that direction and sigma 2 in the direction here. So this is a little element at the top, but sigma 2 in this case, it would be a normal stress in the y direction, and sigma 1 would not be a normal stress in the z direction, but is a normal stress in the x direction. And then obviously you could have the same stress state anywhere around the perimeter or at any point on this pressure vessel. They have the same state of stress, okay? All right. The second case is a spherical thin-walled pressure vessel. And in this particular case, you can probably imagine, you can see it here. We have symmetry on the sphere, right? And so there is no way to identify a hoop or a longitudinal direction. Every orientation of the sphere looks the same in a spherical symmetry, i.e. sphere. So you have the same components, but you still have a biaxial state of stress. It's just the same stress value in both directions, okay? All right. So let's look at this free body diagram. This is actually going to have very much the same free body diagram as we had before. If we look at it this way, oops, I should draw it this way. Exaggerating the wall thickness so I can really show it, right? Still, we have the stress, the force from the stress acting on that hooped wall. And so that is going to be sigma 2, if I can write it. Lord, let me write it. Sigma 2. And the area ID squared on 2. So we actually have the same exact values here. All right. So that is, if you go back and look at the previous page, which I think I can, it's the exact same free body diagram. The only difference is there's a flat wall shown here, and in the other one, it's a curved wall. So we are going to get the same exact result here, that the stress for the spherical thin-walled pressure vessel is going to be the pressure times the inner diameter over 4 times the thickness. All right. And so again, that is, it's the same in both directions, right? It's the same in both directions. Okay. All right. So this one is, you know, pretty plug and chug to do, right? So, you know, really 3 equations, but 2 of them are the same. So in this, you know, if you want to remember the spherical stress, the sigma 2 is P, pressure times the diameter over 4 times the thickness. That works for both directions in the spherical case. And for the cylindrical case, that's the longitudinal stress. The hoop stress is twice that, okay? All right. All right, let's do a couple of problems. Let's stop sharing this. Okay. All right, we're going to do the first problem in chapter 8. So this is 8.1. And actually, it's also a homework problem if I copy it. So I'll do 1 and 2. They're really easy problems. They're just straightforward applications. And then we'll do also 8.7, which is also a thin wall pressure vessel problem, but it uses, it wants you to actually use the same derivation we did here, but we're going to actually use that not to get the stresses in the pressure vessel, but to figure out the force, the shear forces in a rivet line that holds the pressure vessel together. Okay. All right. All right. What's going on here? All right. All right, so let's look at 8.1 and 8.2. I mean, these are so straightforward, they don't even bother to draw a picture for them, right? So for 8.1, they're giving you a spherical pressure vessel, right? And here they're giving you an inner radius of 1.5 meters. They're giving you the internal pressure, and they want you to find the wall thickness if neither of those stresses are to exceed 12 megapascals, okay? We'll just leave it this way. All right. So for the spherical case, right, we know that we just have the same stress in both directions. Right, what the book is using as sigma 2, right? The spherical stress case. So that is the pressure times the diameter over 2 times the thickness. I'm sorry, this is 4. Okay, so in this particular case, they give you the pressure, kilopascals. They give you the radius, so that means that the inner diameter is 3 meters. And they don't give you the wall thickness, but they give you the allowable stress, right? And that is 12 megapascals. All right, so from this equation, right, we know that sigma 2 must be less than or equal to the allowable design stress, correct? So, you know, let's do that in the limit. And if we, you know, put a less than or equal to sigma allowable there, we can get that the wall thickness must be greater than or equal to the pressure times the diameter over 4 times the allowable stress, right? Or in other words, that is 300 kPa times 3 meters over 4 times 12 megapascals, right? And so this will work out, but you remember I've got an extra, you know, I've got a kilo upstairs and a mega downstairs. So that means that we've got a 10 to the minus third down here, which is actually giving the answer in millimeters, or you can write it all out in, you know, pascals and meters, all right? And the number we get here is okay. I get that the thickness must be greater than or equal to 18.8 millimeters. Okay, so you want something probably like a 19 millimeter wall thickness will work on here. Okay. All right. Now, if we had the same exact values, but instead of a spherical, now let's consider a cylindrical one. In this particular case, right? So let's see, we have a cylindrical pressure vessel, right? Where we have the inner diameter here, D. There's a wall thickness of T. Both of those are length, but the length actually you'll see doesn't really matter in this one, right? So if we look at a differential element on the pressure vessel, here, right, we had the same sigma 2 as the spherical case down the longitudinal direction, but we have this hoop stress sigma 1. And we recognize here that the hoop stress is going to equal twice the lateral stress, right? So in this particular case, it's going to be the hoop stress that limits the design, okay? So we will probably need a thicker wall because of the fact that we have a cylindrical pressure vessel, right? In fact, it's going to be twice as thick, all right? So in that particular case, we need to get it, the wall thickness so that the hoop stress is less than or equal to the allowable stress, all right? And in this case, that hoop stress is going to be the pressure times the diameter over 2 times the thickness, right? And that has to be less than the allowable. So that's going to give me, again, that the thickness must be greater than or equal to the pressure times the diameter over 2 times sigma allowable, right? Which you can see is the same thing we had before, except divided by 2 instead of 4. So this is going to give us that the thickness must be greater than or equal to 18.8 times 2. Right? Or 37.5 millimeters. Okay, so clearly, if you have a choice between making a cylindrical or a spherical pressure vessel, you're going to need less material to make a cylindrical pressure vessel. A spherical pressure vessel. The cylindrical pressure vessel is going to require a wall thickness that's twice as much because of this hoop stress. And it just doesn't resolve the hoop stress as well as the spherical pressure vessels do. So that's why if you look at, when you have pressure vessels, say on the International Space Station, because they do have external pressure vessels on those, you will see they are always going to be spherical, right? There are situations where due to packaging, it's difficult to put a spherical pressure vessel in. And so there, sometimes you will see them replaced by cylindrical pressure vessels. And so, if you have to ship these, it's easier to ship the cylindrical pressure vessels. So like if you see out in Hudspeth County, people operate off of compressed natural gas. And so they'll ship like CNG in the cylindrical ones, takes more material, right? But actually it's easier to stack the cylindrical pressure cylinders than it is to stack spherical ones, okay? But obviously needs more material, okay? All right. Any questions on those? So those are pretty straight up applications, right? It's pretty plug and chug. Let's look at a problem that's a little bit different. So let's look at 8.7. All right, so here's problem 8.7. All right, so this is the cylindrical pressure vessel, right? They say it's a boiler, but the way this is being constructed is they're taking a single piece of sheet metal and bending it around to be cylindrical. And then there's a double plated seam here. I'm writing over it, so now it's impossible to see, right? There's two plates that are riveted together through the bent center plate, and that closes off or seams up the boiler, okay? All right. Now, fine, they give us the thickness of the plate. The boiler bent plate is main 8 millimeters, and the covering gusset places are also 8 millimeters. And the rivets are given a diameter of 10 millimeters and spaced 50 millimeters apart. Okay. They give you the internal pressure. They want to find a couple things here. First, find the circumferential stress, the hoop stress in the boiler plate away from the seam, like what you would see up here. That's the first part. The second part is to find the circumferential stress in one of these plates, okay? These cover plates along the rivet line. And then the third one is to figure out the shear stress in each rivet, okay? So what's the thought process here? If you're designing this, if you're going to design this, and this is your design concept, where will it fail first? Okay. It could fail in the rivets, right? A rivet could fail. All right. It could also fail in the cover plates, but you'd say, well, look, there's 2 cover plates, so the thickness is twice as much as in the main bent part. So clearly it should fail in the bent part before it fails in the cover plates. But the cover plates are somewhat compromised because we have the rivets in there, all right? So both there's an area reduction, and honestly, if you want to get technical about it, we probably should apply a stress concentration factor in here. Although I don't think we have enough information to do that. So, but we should probably do both. So you don't know where it's really going to fail first. This is the difference between how we simplify problems down in this class typically and how you actually have to think about design problems as a mechanical engineer. So as a mechanical engineer, your boss is not going to come in and say, hey, I need you to calculate the sigma 1 stress in the middle of the center plate. They're going to tell you, okay, design this so it doesn't fail, okay? Well, you need to do all of these calculations and probably more, all right? And it's not as if it's just one calculation, but there's multiple ones, and you might have to iterate on these, right? So, okay. But anyway, let's go through it. So let's do the first one. The first one's pretty easy, so we'll do part A. All right. In fact, what time is it? I think we have time. Let's put everyone into groups and let's have you do part A. So you have to figure out, so this is cylindrical, right? So here, part A, they want you to find the hoop stress, the sigma 1 stress, right? Which is PD over 4 times, I'm sorry. What's this? 2 times the thickness, okay? So I'll put you into groups and let's see if you can do that one. I will not give you a ton of time on that one because it's pretty, you know, like I said, it's pretty straightforward. Probably take me longer to break up into those groups than to do anything else. All right, you're not going to have to post this photo onto Gradescope, okay? But just still do them in a group. All right. Open all those. So I'll give you about 10 minutes to do that, okay? Which should be plenty of time, all right? And then I'll pick one of the groups to actually present the results. All right, I think everyone's back. It looks like, okay. So, all right, what was the answer we got? All right, let's ask. All right, let's do group 7. So folks in group 7, Andrea, Angel, Jose, or Oscar, what did you get as the hoop stress, the circumferential stress in the main bent plate for that problem?
It was 127 megapascals.
Yep. Yeah, 127 megapascals. That was pretty straightforward. The pressure is the 2.5, right? The diameter, they give you the inner radius is 0.75, so the diameter is 1.5, and then the thickness is the 8 millimeters, right? So that comes out to be exactly that, right? Okay, so let's talk about the second part of the problem. And let me set you up a little bit on that as well. Let's see this anymore. So let's talk about part B. In part B, right, they want you to find the circumferential stress in one of the outer plates along the rivet line, okay? All right. So again, this is a very good example of, why it is important that, there are these design equations, MC over I, P over A, in this case, PD over 4T, whatever it is, that you can kind of just recite and quickly compute answers for. But the derivations for all these now, at this point in time, you should start to be able to analyze what are the stresses that they're talking about in part B. It's not going to be just the straightforward PD over 2T, where T is going to be, simply the thickness of one of those plates, right? We have to look a little bit from a force balance, all right? So let's see if we can zoom in here, and I'm going to try to draw this a little bit better. So let's imagine, right? You got this rivet line, okay? So there is a sort of a cylindrical disk of symmetry here. So you can see how these red lines are supposed to indicate center lines between the rivet line, the two rivets in the rivet line, 3 rivets in the rivet line, okay? So these are planes of symmetry. Everything is symmetrical about that, right? What happens at this rivet is the same as what happens at this rivet at this rivet. All right, so let's look at the free body diagram in that particular case. I will try to draw that somewhat neatly. All right, so we have, I guess we should do it this way. Here is the symmetry line. Okay. All right, so those are the two hemispherical lines of symmetry, right? So right in the middle, we're going to have a rivet, right? Here's the rivet. We know this spacing here is the same as the rivet spacing. So this is 50 millimeters. And we know that the rivet is 10 millimeters. So this has a diameter of 10 millimeters, right? Here is the rivet. All right. Now, up here, we have the top of the end plate, right? And so this is kind of like the end plate here, right? And then up above is the stop. This computer's acting so weird today. Right, up here is the main plate. Okay. All right. So where do we want to calculate the stress? they want us to do this right along the rivet center line. So looking at a differential element of stress like right here. All right, so we can do the same analysis to figure out the forces acting on there, right? And they want the hoop stress. They want this one. That's sigma 1 stress, okay? All right, so if we look at this from the side view, so to speak, right? Here is the center plate, the gray plate, and then up here, we have one cover plate and then the other cover plate, okay? All right. So, and now let's consider this just to be, all right, here's the rivets acting on here, right? So we can consider this to be just in this 50 millimeter spacing if you want to, all right? All right. So what is the net force that wants to pull the gray plate to the right? That is going to be the pressure acting over one of those little C-shaped sections like this, right? It's that force where this is going to be 50 millimeters, correct? So here is the pressure acting on this, all right? And this distance here is the full diameter, okay? So this force is going to be the pressure times the diameter times that 50 millimeter spacing. All right, that's the force acting here. We'll call that force in the plate. Force in the plate, right? Okay, now what's going to counter that? Well, obviously, half of the force in the plate on each one of these, right? So you're going to get the force in the plate over 2, and then the force in the plate over 2 on this one. In each one of those cover plates, correct? But, you know, let's see if I can draw that a little bit better. If we actually look at the area that the hoop stress resides on, if I were to kind of zoom in, we have to consider the area reduced by the bolt, the rivet diameter. Let's see if we can draw this reasonably well. All right, so this is one of the cover plates. All right. This is still 50 millimeters, right? Acting here is going to be, well, really, if you want to do it this way, right? These two added up together is half of the force in the gray plate. So this is really force of the plate over 4, force in the plate over 4, correct? And the stress we get there is that force acting over this reduced area. Okay? So you can't just apply the same equations that are boxed in the text or that I just derived, but we can use the same analysis to figure out that stress, right? This is the face that the sigma 1 stress acts on, okay? All right, so I think you now have enough information to actually calculate the hoop stress in one of the cover plates at the rivet line with the reduced area due to the rivet hole, okay? So I'm going to send you off back into your groups. Well, before that, do you have any questions on this before I let you run the numbers? All right, so let's bounce you back into the groups. All right. Okay, now that everyone's back. All right, so to do part B, what did you get as the force in that, considering just the 50 millimeters, that's that spacing, what's the force that wants to pull the gray center plate away from the two cap plates? Awkward pause commences. I already know the answer, so, but maybe somebody can tell me.
Is it 79.1 megapascals?
Well, it should be a force. It should be a force, right? What's the force that wants to push that gray plate away?
Oh,
What's the force that acts on that, plate?
63.
What did you get?
63. 63 kPa? No.
It's going to be in units of like newtons or kilonewtons or something like that.
Is it 50.625 kilonewtons?
You divided it by 2. Why did you divide it by 2?
I didn't.
What did you use for did you use the radius for the diameter?
I used the 0.05. Well, meters times the 0.008 meters times the stress.
Oh, okay. All right. All right. No, you got to remember, right? You have here's like the rivet spacing. So there's this gray, half of the gray cylinder, right? All right. And imagine this is 50 millimeters, the paper thickness. All right. The pressure acts on this back face, the diameter times the 50 millimeters. And that puts a net force that wants to push half of that pressure vessel away, correct? So what do you get for that total force? Right, let's go back and all right, anybody get it? I drew the picture, right? So okay. So we have the gray cylinder, and we're going to cut it and consider just the 50 millimeter segment of it, right? So we get this sort of C shape. Does that make sense, right? The pressure exerts a net force on that gray plate, pushing it that way, right? That is going to be the pressure acting over the projected area, this area here, just like we did the other derivation. So that force, this force here, that net force is going to equal the pressure times this projected area. What's that projected area going to be?
Diameter times the spacing.
Yeah, so it should be the diameter times the spacing. So if we put in the numbers there, it's the 1.3. What was the pressure again? 1.35. Yeah, 1.35 megapascals. Okay. The diameter is 1.5 meters, correct? And the spacing is 50 millimeters or 0.05 meters. And that's going to give me an answer. $101 kilonewtons, right? Kilonewtons. That's the net force. All right. So, right, it's the blue plates that are going to resist that, right? So basically, the force acting here in half of this gray plate is going to be half that, which is the number that you said first was 50.6, right? Which is why I thought that's what you were giving me, right? All right. Does that make sense? This is the force that's, resisted by the thickness of that gray plate, right? Okay. Does everybody see that? I can't see your pictures because like 80% of you don't have the cameras. Nobody's saying anything. So I don't know. All right. Well, whatever. Okay. So basically, right, this is going to be the 50.6 kilonewtons acting that way, right? That's what, if you look at one of the rivet lines, it's that force there is the 50.6. Okay. All right. All right. Now, that one is going to be balanced by, you can think of it a couple of ways, but right? So we've got in each one of these blue plates, half of that, which is going to be the 50.6 divided by 2 again. So it's 25, this is 25.3 kilonewtons acting over this whole reduced area here, right? So that means that the sigma 1 stress is going to equal 25.3 kilonewtons over 2, because we have the 2 plates. All right. And then the area is this reduced area here. So that is going to be the spacing, 0.05, minus the hole diameter, 0.01. That's in meters, times the thickness, which is 8 millimeters, or 0.008 meters. And when you do that, we get a stress here of 79 megapascals. Okay, that's that. Now the last part asks you to figure out the shear and the bolt. Okay, you've got the same force. It's pretty easy. It's acting in double shear, right? So the shear force in each bolt is going to be half of this, or again, the 25.3 kilonewtons, and it's going to act over the bolt diameter. Okay? All right. Well, that's it. That's pretty much the end of class. So, okay, very good. We'll see you Thursday.